This video is about geometric growth and decay, also known as exponential growth and decay. Because there's n in the power, I've got some number to an unknown power. So these are the formulas we learnt when we did geometric sequences and series earlier. So we've got the t formula, ar to the n minus 1. We've got the Sn formula, depending on whether our r is greater than or less than 1. This formula is exactly the same formula. It's just useful if the denominator is a positive number. So if this is bigger than 1, you get a positive number. If r is less than 1, using this one gives you a positive number, but it's the same formula. Technically, you can use either formula. They will both give you the same answer. And remember, we've also got this limiting sum formula. So if our sum continues to infinity, we can use this formula, but only if the absolute value of r is less than 1. If it's not less than 1, then there is no limiting sum. My first two examples are actually going to use this formula. They're going to be series to infinity, so that's the one we're going to be using. So here's my first example. We're going to express 0.57 recurring as a fraction. So with this one, it's just the 7 that repeats. So 0.577777 ... So one way to do this is to express it as a series. So we've got 5 on 10, 5 tenths, plus 7 hundredths, plus 7 thousandths, plus 7 over 10,000, and that's going to keep going on forever and ever and ever. Now this part here is a geometric series with the first term equal to 7 over 100, and the common ratio is 1 on 10. If I divide that by that, I'll get 1 on 10. So it's a geometric series. We can use our sum to infinity because our r is less than 1, and it does go to infinity. Okay, so what we end up getting then, the 5 on 10 is still there. Now if this was just 0.7 recurring, that'd be 7 on 10. It would change our a to 7 on 10. It wouldn't change the r. You can do any recurring decimal in this method. Okay, so this part, I want to use that a1 minus r formula to find the sum of all of that. Now because it's fractions, I'm going to write it as a divided by 1 minus r. So I've got 7 on 100 divided by 1 minus a tenth. Okay, so 5 on 10 plus 7 on 100. Now 1 minus a tenth is 9 tenths, but I'm going to change it to timesing by 10 on 9. Okay, just dividing fractions. Let's cancel a 0 there, divide the top and bottom by 10. So just hold out on that one for a second. This becomes 7 on 90. So if we're going to get a common denominator, I need this to be 90 as well. So I'm just going to go times 9 times 9. So 5 on 10 becomes 45 on 90. Okay, so I've got my common denominator, add the numerators. So 45 plus 7 is 52 on 90. And that can also simplify down to 26 on 45. So 26 on 45 is 0.57 recurrent as a fraction. Now, just a little tip with calculators these days, it can do it for you. It can literally do it for you. So if you just put in 0.57, sorry, it's a bit dark, and you press the 7s until you go past the end of the screen and press equals, there you go. But to get marks in an exam on that, you need to show you're working out. It's a good way to check your answer, but you can't do that in an exam and expect to get full marks. Okay, here's a second example. Now this is this type of question is often either a ball bouncing, in which case you get a geometric series of the up bounces and the down bounces, which because an up bounce and a down bounce are the same, you can just double the up bounces. That's a common, and then there is an example like that in the textbook. I'm going to do one where a stone is skimmed over a lake. it initially lands 9 meters away and then travels 1/3 of the distance after each bounce. How far does it travel altogether? So let's write out that series. So its distance is the initial 9 meters, and then it travels 1/3 of the distance, so plus a 3, and then a third of that, plus 1, and then a third of that, and so on and so on and so on. So again, it's a geometric series. Our A this time equals 9, and our R, if I do that divided by that, is 1/3, which is that 1/3 of a distance. Okay, it does go to infinity, so again we can do our A over 1 minus R. So that's 9 over 1 minus 1/3. Okay, 1 minus a third is 2/3. So 9 divided by 2/3 is the same as 9 times 3 on 2. And that equals 213.5 meters. Okay, I've got a couple more examples using our other formulae. So these ones don't go to infinity. So, well, it's just one more example really, but different parts. So we've got a $3,500 computer, and it depreciates by 40% per annum. So each year 40%. Find its value after 1 year. Now, whenever you're doing percentage questions in this course, it is strongly advised by me to write them as a decimal. So that is 0.4. If you can always put 40% or 40 over 100 into your calculator and ask what it is as a decimal. The harder problems will be much easier if you use decimals rather than percentages. Okay, so we have to find its value after 1 year. So it's going to depreciate by 40%, which actually means the remaining value after a year will be 60% of the original value. So we do 1 minus our 40% to get our 60%. So after 1 year, it's $3,500 times by our 0.6. So 3,500 times 0.6, which is $2,100. So after 3 years, we started with our 3,500. We times that by 0.6 for 1 year. And then our answer to that will get multiplied by another 0.6 for the second year. It'll be 60% of this. And then for the third year, it's 60% of that whole answer. So times that by 0.6 again. So 3,500 times 0.6 to the power of 3. Okay, 3,500 times 0.6 to the power of 3, which equals $756. Okay, so after 3 years, it's worth $756. Now, we're going to look at this, the computer's value after n years, as a geometric sequence and determine its value after 15 years. So after 1 year, all right, after n equals 1, it was worth $2,100. When n equals 2, that was 3,500 just times 0.6 times 0.6. That actually gives you 1,260. N equals 3, we got this 756. And this is a geometric sequence because there are no plus signs. So our A is 2,100. Okay, it's not that 3,500 that we started with. It's after 1 year is the first value of our sequence. And our R is 0.6. Okay, it asks us after 15 years. So if we're doing it like a geometric sequence, we want to know, use our Tn formula. So our Tn is AR to the n minus 1. Okay, so in this case, our A is the 2,100. We're looking for T15 after 15 years. So, oh, too many zeros. Multiplied by our R is 0.6 to the power of 15 minus 1, or 14. Now be a bit careful. Think about it. Are you allowed to do 2,100 times 0.6 first? No. Remember your order of operations. powers come before multiplications. It's a very common mistake. Do not multiply these two. Powers come first. But in this particular case, you can just throw all of that into your calculator. And if you throw all of that into your calculator, it's going to be way down to $1.65 after 15 years. Lastly, we talk about a thing called scrap value. Our scrap value is basically when it's worthless. So the computer's considered worthless when it's worth under $100. Now we know at 15 years it was $1.65, so this is less than 15 years we're talking about here. After how long is it considered to be worthless? So what we want to do here is actually find the value of n when our Tn equals 100. So using our Tn formula, our AR to the n minus 1 equals 100. Remember our A was the 2100. Our R was 0.6 to the power of n minus 1 equals 100. Now we just need to solve this equation. Now remember, you cannot multiply here. You need to divide each side by 2100. So 0.6 to the n minus 1 is going to be 100 over 2100. If you simplify that down, that's 1 on 21, just cancelling some zeros. Now when an unknown is in the power, remember we take the log of each side. Now it doesn't matter which base log you use. You can use any base log because it really is exactly the same thing as long as you're doing exactly the same thing to both sides. I normally use log base E, but you can use any log you want. Now remember that log laws, when you've got a power, the n minus 1 comes down the front. So really nice little log law for solving this type of thing. So we end up with this. And then we can just divide each side by log 0.6. So we've got our log 1 on 21 divided by our log 0.6. Just throw that in your calculator, you get 5.96 for n minus 1. Add the 1, n equals 6.96 years. Sorry, my camera got a little bit out there.